could front it up.
Oh, yeah. Oh, you have no idea. You have no idea.
All right, I guess we get started then. Yeah, so it's great to have Professor Tom Maccarone visiting us today. He got his PhD from Yale and then did a couple of postdocs in Europe and Italy and in Amsterdam before he was hired as faculty at the University of Southampton in the UK. He spent a good number of years there before Texas Tech came and stole him away a couple of years ago. So yeah, he's been instrumental in building up the astronomy group at Texas Tech over the last couple of years. And his research interests, as well as I've heard him, I think, tell other people, he likes to study all things that accrete. And so in particular, he's an expert when it comes to compact object populations, especially Pulsar clusters. So yeah, I look forward to hearing about it.
Okay, thank you, Janelle. So before I get into the nitty-gritty of the research, I'd like to thank a few collaborators who made this work possible. There are many more people who contributed to some of the stuff I'm going to talk about, but these are the ones who are really the key players. So Arno Kundu, who does some stuff with Eureka Scientific and also is a faculty member at the Tata Institute for Fundamental Research in Mumbai. Steve Zepp at Michigan State, Kathy Rohde at Indiana, Mark Peacock, Jay Strader, and Laura Chomick at Michigan State. I should mention Mark was my first PhD student, and James Miller-Jones, who I call Jimbo, but not very many other people who's at the Curtin University of Technology in Perth, Australia. You have to know him to call him Jimbo. All right, so let me give an overview of what I'm going to talk about. So I'm going to start off by, well, first I'm actually going to start off by giving a little bit of the motivation for understanding what goes on with binary stars. So I think this is an area that isn't something that a lot of people work on here, and I'd like to really try to impress upon everybody why a lot of stuff involving mass transferring binaries is really fundamental to other areas of astrophysics. But then I'm going to talk about an overview of the dynamic of star clusters, how we go about finding black holes out in nature. And I'll talk about the way we find the stellar mass black holes. If you want to know about the supermassive ones, you can ask Janelle. Talk about X-ray sources in extragalactic star clusters. The first Glavier cluster black hole, for which there's really strong evidence, and then opening the treasure trove of Glavier cluster black holes in our own galaxy in recent years. And along the way, I'll talk about some fundamental physics that we can do using Glavier cluster black holes, and some supernova physics and some galaxy evolution. So I tried to add a couple of slides focusing on the galaxy evolution, because I think that lines up a bit better with what a lot of people... No? Okay. Well, I'm going to do it anyway.
Right.
All right, so importance of close binaries. So this is not going to be an exhaustive list, but it may leave everyone exhausted by the time I'm done with it. Okay, so one is that these are the best places to understand black hole accretion. So we can look at black hole accretion either in stellar mass black hole systems or in supermassive black hole systems. But the stellar mass black hole systems give us a lot of key advantages. So one is that a lot of them have masses that are known to much higher precision than we know almost any of the supermassive black hole masses. And the best constrained supermassive black hole masses, I think, are mostly the maser ones, where most of the accretion is sitting behind a big cloud of dust so you can't see it. But one of the other really important things is that the stellar mass black holes show strong variations in their accretion rates on timescales that are accessible to humans. And by strong variations in the accretion rates, I mean factors of millions in some cases. And by human timescales, I mean of order years or less. The viscous timescale from the inner edge of the accretion disk around a small supermassive black hole is a few decades. And so what that means is that if you want to understand kind of climate in black hole accretion, you need to look at the stellar mass black holes. You can't get a long enough time baseline on an AGN to really understand what happens when things change in dramatic ways. If you want to understand weather, what happens on really short time scales that makes the small variations, it actually turns out that you get better constraints from the AGN. Okay. Another thing about close binaries with compact objects. So type 1 supernovae are, of course, an example of this. And I was actually intentionally wrote type 1 rather than type 1a there. So I think everybody understands that type 1a supernovae form when a white dwarf grows above the Chandrasekhar mass. But an interesting point is that the type 1b and c supernovae probably require a close binary companion in order for the envelope to get stripped in a useful way. And so probably all type 1 supernovae are in relatively close binaries. Millisecond pulsars and precision tested general relativity. So millisecond pulsars are neutron stars which are spun up by accretion, and that allows them to have very fast spin rates even when they're quite old and have low magnetic fields. And these are one of the best places that we have for testing general relativity. So for example, I don't know if any of you heard of the Pulsar timing array project. Everybody? No, not the grad students? Okay. So this is a project where what they're doing is they're looking for very long wavelength gravitational waves, so longer than what people look for in the kind of laboratory-based things like LIGO. And so these might be gravitational waves from supermassive black holes in spiraling, or maybe from some cosmological effects in the early universe. And the idea behind that is what you can do is you can use the pulsars as clocks, and if you see correlated deviations from the normal pulsar spin down among a large number of pulsars, you can infer that a gravitational wave probably actually passed by the Earth rather than the pulsars. And so the Earth is being moved back and forth by the gravitational waves. And this is something that you can only do with the millisecond pulsars, which are products of binary stellar evolution. And then gravitational wave sources. So if we look at what LIGO is trying to find, it's either in-spiraling neutron stars, in-spiraling black holes, or millisecond pulsars of a particular kind with mountains on them. And so these are all things that form through evolution of close binaries with compact objects. Short gamma ray bursts are also thought to be mergers of two neutron stars, which are again close binaries with compact objects. Thorne-Shigkov objects. So these are a weird kind of star that has a neutron star core. Everybody's looking at me with a blank stare like they've never heard of these before.
Well, Anna comes here a lot. So
Oh, okay.
A lot of us know it, but
Oh, okay.
not everyone.
Okay,
So-
yeah. Okay, so Thorne-Shigkov objects, the idea is that these are hypothesized, and there's been a suggestion about a year ago that there's a real one. So the idea is that if you have a merger between a neutron star and a red giant, that neutron star will sink to the core of that red giant, and it will. There's a lot of debate about what happens next. So in the early calculations by Thorne and Shigkov, they suggested that the thing would puff up like a really extreme red giant, and it would look basically like a red supergiant, but it would get some abundance anomalies from the nuclear fusion on the surface of the neutron star. There have been some other suggestions that neutrino cooling would make that whole thing evolve in seconds, and it would actually look like a kind of gamma ray burst, and we'll never actually find these. So Emily Levesque has put forward, I think, the best candidate for one of these about a year ago. I've done some digging, and I think it has a proper motion in old proper motion catalogs, and she was arguing it was in the Small Magellanic Cloud. So I think it's actually a foreground star, and I can talk to people outside of the colloquium about that if you're interested. R process elements, so we have all these, S process elements made by slow neutron capture, and we have a lot of ideas about how to do that. The R process elements made by rapid neutron capture, we know they exist, but it's hard to find a channel for producing them. It may happen in supernovae, although that's fairly controversial. It may happen in double neutron star mergers, or it may happen in something like a Thorne-Shigkov object. All right, and then something interesting that has kind of been coming up recently is that X-ray binaries may actually be the source of reionization of the universe. And so Tassos Fragos, who's in Geneva, has been doing a lot of work on this lately. And the idea is that you should probably produce a lot more X-ray binaries per unit stellar mass in the early universe than you do now. And the black holes that are produced in the early universe may be a little bit heavier than the ones that we have now. And that combination may lead to more X-ray binaries per, more X-ray luminosity per unit stellar mass in the early universe than what we have now. And at the same time, in the early universe, it's very hard for the ultraviolet photons from star formation to escape their host galaxies. Now, it turns out this is something that I kind of noticed and pointed out to Tassos, and we've at least been talking about writing it up. In the early universe, you haven't produced much carbon or oxygen yet, and the main source of opacity for soft X-rays are actually carbon and oxygen edges. So the X-rays from the X-ray binary should actually be able to escape the host galaxies very effectively. And so this may be a way around one of these problems that people have, that we know the early universe got reionized fairly quickly, and there isn't enough AGN luminosity to do it, and the star formation light can't escape. So this is something to keep an eye on, although I'm not sure it's correct yet.
Why are there more binaries in the early universe? Just because things are denser? Or?
No, just because the rate of star formation to total stars is higher, and in young star-forming populations, you produce a lot more X-ray binaries per unit stellar mass than in old stellar populations. Basically because you can get wind-fed accretion from the companions. And so when you have massive companions with strong winds, then you can have fairly wide separations and still get accretion. Otherwise, you need to wait until Roche-slope contact takes place. A few things without compact objects. So I have a paper I'm just going to briefly mention. I'm going to talk about this a little bit later too. There have been a bunch of claims of IMF variations. This seems to be something that comes along every 10 years and then people decide they don't believe it. But there have been a few strong claims in the last 5 years or so about variations in the initial mass function of stars as a function of galaxy type. And most of it has been based on something called the wing forward band, which is a particular iron hydride band, which is out in the far enough in the infrared that basically only M giants and M dwarfs are contributing a lot of light, and it's a pretty good differentiator between M dwarfs, which have a strong wing forward band, and M giants, which don't. And so basically, mostly based on that, and now with some other lines as well, people have been claiming that there are very strong IMF variations and certain galaxies are extremely dwarf heavy. Something I pointed out a couple years ago is that there is a class of stars called S stars, which are formed through binary evolution, that can have very strong wing forward bands also, and they actually are a few % of M giants in our own galaxy, and they should probably have some correlation with the stellar density of the galaxy that they're in, because they're formed from extremely wide binaries, which can get disrupted in dense galaxies. Another thing is mergers of massive stars may be quite important for the initial mass function. So this is something that Uxana, it was in I think it's Louvain or Leuven, I'm not sure which way to pronounce it I'm supposed to use, but it's in Belgium, has been pushing. Yeah, he speaks French, but it's a Dutch university and it confuses me now. Anyway, so he's done a lot of observations of young stellar associations and shown that the binary fraction of the massive stars is huge. And given that, most of the things that we think are single O and B stars are probably actually the products of mergers of O and B stars with one another. And that suggests that the initial mass function may be thrown off by that, but it also may lead to funny type 2 supernovae that come out of the products of those mergers. And of course we have the blue stragglers, which is a long known problem that if you look at old star clusters, you see some stars that seem to be along the main sequence but above the turnoff. And those basically have to form through some kind of binary star process. So there are all, so again, this isn't an exhaustive list of things where binary stars are important, but it's I think a fairly large one, and I hope I've convinced everybody that if you really want to understand what's going on in a stellar population, you need to understand the binaries and not just treat binaries as two single stars that happen to orbit one another, because a lot of times they interact. Now let me give some motivations for understanding binary stars in clusters. Okay, so this is an image of 47 Tucanae, and one of the things that and this is actually the first light image from the Southern African Large Telescope. And one of the things that you can see in this image is that the density of the cluster falls off towards the outside, but in the inside, and this is not just saturation, in the inside there's really a core of constant stellar density, or pretty close to constant stellar density. And early calculations of what should happen with star clusters suggested that they shouldn't have these big puffy cores, that they should just have roughly a power law density all the way into the center. And some clusters have that, but most of them don't. And the suggestion for this is that binaries are acting as an energy source in a way that's similar to the way that nuclear fusion acts as an energy source in a star. If you think about what a star would do without nuclear fusion, it would collapse very quickly towards the center, right? But because there's fusion in the core, that provides an energy source that essentially heats the core and holds up the collapse. In a globular cluster, what's going on is that there's something called Heggy's law, which is named after Douglas Heggy, who's at the University of Edinburgh. And it was named after Heggy by other people. He's actually a very modest man. But Heggy's law says that hard binaries get harder and soft binaries get softer. And the basic idea is if you think about the orbital speed of a binary star, if the orbital speed is faster than the speeds of the stars nearby, when a third star flies by and interacts with the binary, what will happen is the binary will transfer energy to the third star. So the third star will have a velocity that's now closer to the velocities of the two other stars. And that takes energy away from the binary, and what it'll do then is it'll contract. Right? So anytime you have a close binary, at whatever rate stars interact with it, it injects energy into the other stars in the cluster. When you have wide binaries, they quickly get disrupted. So if we look at globular clusters nowadays, they actually have very low binary fractions. This is actually a matter of quite a bit of observational uncertainty, but the binary fractions are typically a few to 10%, depending on which cluster and whose numbers you believe, which is a lot lower than what we see in the field. But the number of close binaries, as I'll talk about during the talk, like X-ray binaries and cataclysmic variables, is actually a lot larger than what you get in field star populations. So what you're left with is a lot of really close binaries and very few wide binaries. And that's a consequence of Heggy's law. And that energy injection from scattering off of those binaries holds up the collapse of the cluster. Okay? This color magnitude diagram here is of, I think this is M4, but I'm not sure. So this is shows a main sequence, a turnoff, a giant branch, some horizontal branch, and then there are these stars here, the blue stragglers. And like I mentioned on the previous slide, those shouldn't be there according to normal stellar evolution if we have a single age cluster, but they are there, and we think that they form through binary stellar evolution. Okay, and here I have a kind of artist's impression of a gravitational wave source. And this is something that also I think is going to turn out to be quite important in globular clusters. If we have globular clusters, as I mentioned before, have a lot of close binaries compared to what we see in field star populations, and therefore they're good places to form the close binaries that might lead to mergers in gravitational wave sources. And in particular, another thing that we have going for us in globular clusters is globular clusters are low metallicity. And at low metallicity, we think stellar winds are weaker, and that can lead to more massive black holes being formed from a normal supernova process because at the time the core collapses, the star hasn't lost as much of its envelope. And in globular clusters, we can get stars into close binaries that weren't born there. Right? And so when we have a close binary star in the field population, what will often happen is something called a common envelope evolution. First star evolves off the main sequence and it engulfs the second star, and then the two cores kind of sink in together and eject both envelopes, and we lose a lot of mass from the final black hole in that process. And if we look at the calculations from theory about what the black hole masses should be, they tend to say 15 to 20 solar masses. If we look at the masses of the black holes that we've actually measured so far in the solar system, they're almost all right around 8 solar masses, and that suggests that common envelope evolution really is reducing the black hole masses. And so we have two ways that we might get black hole mergers in globular clusters that have heavier black holes than what we see in field star populations. This is extremely important for something like LIGO, because LIGO is flux limited, and the flux in gravitational waves is a fairly strong power of the masses of the objects involved, and so you can really expand your horizon distance a lot by cranking up the typical black hole mass even by a factor of 1.5 or 2. So this essentially would bring us way out to cosmological distances if we can get these kinds of things. And this is actually another interesting point, which is if you get really good gravitational wave measurements at cosmological distances so that you can get the masses of the two objects, you can use them as standard sirens. Right? And the idea behind that is that it's kind of like a standard candle, but it's actually a lot cleaner than a standard candle if you can get small statistical errors, because dust doesn't affect gravitational waves. Essentially, the only thing that will affect gravitational waves on the way from the source to you is gravitational lensing, which also affects any electromagnetic signature you might like to use. So if we can get this kind of a method to work, I think it immediately supplants a lot of the stuff people are doing nowadays on trying to measure distances in the universe. Okay. All right, so I'm going to focus on the search for black holes in globular clusters. So let me talk a little bit about the history of black holes in globular clusters. So there were a couple of papers by this guy named Weiler in 1965 and 1970 where he suggested that globular clusters were quasar remnants. And this is, of course, a sort of ridiculous idea now. At that time, people knew that globular clusters were the oldest structures in the universe, and they also knew that quasars were the things at the highest redshift that had ever been observed, and by a ridiculously large amount compared to the highest redshift galaxies at the time. And so at that time, it maybe wasn't quite as ridiculous as it seems in hindsight. But that idea never really caught on. But in the mid-70s, there was a flurry of activity talking about whether globular clusters might have intermediate mass black holes. At first what happened was when they started doing the first imaging X-ray surveys of the sky, they found 4 globular clusters that had strong X-ray sources in them. And that was 4 more than you would have expected if globular clusters produced X-ray sources at the normal rate per unit stellar mass. Right? You basically expect nothing in the Milky Way if there weren't some enhancement due to something in the cluster. And Bacall and Ostreicher suggested that the X-ray emission might be bonding accretion onto central black holes. Okay. And then around the same time, there were some papers that came out suggesting that the velocity dispersion of M15 was shooting up towards the center. So Newell, DaCosta, and Norris did this in '76. So they looked at velocity dispersion as a function of radius, and they saw a huge spike upwards in the velocity dispersion towards the center of the cluster, but they didn't see a spike up in the amount of light that was enough to make up for it, so they had a dark central mass. Now, Illingworth and King almost immediately pointed out that there was another way that you could do this, which is this process called mass segregation that I'll talk about in a bit, which should make the white dwarfs and neutron stars, which are the heaviest objects in a cluster, sink towards the center of the cluster. And the mass to light ratio of a white dwarf or a neutron star is extremely large, so you could get a dark central mass that was actually composed of a large number of stellar remnants rather than a single black hole, and the data were not good enough to distinguish between those two. Something that's interesting, and maybe a lesson for students and maybe even faculty in the audience, is that in the 90s, in the late 90s, basically this paper was rewritten with HST data, and this paper was written with big numerical simulations, but there were basically no new real physical insights in the new papers, and these papers were not cited in the new papers. So occasionally people did what you want to do 25 years ago, and I think, to be fair to the people who didn't cite the old papers, there had been so much time in between that work and their work that I think a lot of the community had lost memory of what had been done. But if you work with ADS, it's usually easy to find these things. So anyway, what happened was very shortly after all this work was done, they found what are called type 1 X-ray bursts coming from all of the Glavier cluster X-ray sources. And these are basically flashes where the X-ray emission shoots up for around 10 to 100 seconds to a luminosity of about 10 to the 38 ergs per second. And that's the Eddington luminosity for a neutron star. And the idea was that these were just thermonuclear runaways on the surface of the neutron star. So very similar to classical novae, except happening much faster and at X-ray luminosities because they're happening on a neutron star instead of a white dwarf. And that basically settled the issue that people said, okay, we haven't seen any evidence for black holes in any of these clusters now. And actually all of the X-ray sources that we've seen are clearly neutron stars. Okay. All right, now I'm going to pause here. I don't like to embed movies into the talk because it usually doesn't work. So now I'm going to show a movie made by, what's his name, Sharav Chatterjee, who's, last I checked, he was a postdoc at Northwestern. And he's got some Star Wars type graphics. Somebody have it? Yeah, let me pause for a second and see if I can. Yeah. So what this is going to show is kind of something about how star clusters evolve, and it's going to show that some of these stars get thrown out of the clusters at various points too. So you can see every once in a while stars just getting thrown out of the cluster by interaction with the other stars. And that's kind of the main point I want to get across from this movie. There's some color coding of different types of objects in there too. But yeah, one of the other points I want to get across is that in the last year or two, people have been able to do full n-body calculations over 10 gig-a-year lifetime of clusters that have the same number of stars as kind of typical Glavier clusters. And this has mostly been a result of people, and that's mostly been a result of GPU calculations really enhancing the numerical capabilities of computers. So we can all thank the people who make computer games for our major advances in science in the last few years. Okay, so now I want to give some intuitive ideas about how the dynamics of star clusters work. So it's useful in some ways to think about these as gases of stars. So then we have a few characteristic timescales. So one is the crossing time, and that's just the amount of time it takes a star to move across the cluster. The next is the relaxation time, and the relaxation time is basically if you take a velocity distribution that's Maxwellian and you perturb it a bunch, how long does it take to relax back down to a Maxwellian distribution? And that follows this kind of complicated formula, but it's something that scales with the crossing time and with the number of stars in the cluster. And for a typical Glavier cluster, it's of order 10 to the 9 years. And then the third is the evaporation time, and that's the amount of time it takes for a star cluster to evaporate itself even in the absence of any tidal fields. Okay? And this number appears fairly exact. I put 136 relaxation timescales. And of course, we don't know it to that level of precision, but that's sort of useful for remembering where it comes from, which is that if we look at a Maxwellian distribution that's self-gravitating, the things that are above twice the mean velocity are also above the escape velocity. And those are the things, and 1 out of every 136 stars in a Maxwellian will be above twice the mean velocity. Right? And so what happens is you evaporate those out, and then you refill in this high velocity mode on a relaxation timescale, and this process repeats until the thing is evaporated itself. So on a order 100 relaxation time scales, a cluster should evaporate itself. So that gives us 10 to the 11 years for a typical Glavier cluster, and that's why they're still there. But this also gives us some insight into why we don't see any very old, low-mass open clusters in the Milky Way galaxy, because they'd evaporate themselves. Now, tidal effects can also accelerate this process, but even without any tidal effects, we wouldn't have any old open clusters. Okay, so now I want to talk about mass segregation. So stellar interactions lead to energy exchange in star clusters, and so the kinetic energies of the stars approach some kind of thermal distribution. And as a result, the heaviest objects then have the lowest velocities, and then they'll have the lowest migrations away from the center of the cluster, and they'll sink to the center of the cluster. And this is what we mean by mass segregation. That if you look at a star cluster, the heaviest things should be sitting in the center, and the lightest things should be sitting on the outside. And this is only true in a statistical sense. There'll still be some M dwarfs sitting at the bottom of the cluster potential, but they'll be preferentially towards the outside. Okay. Now for black holes, you should get severe mass segregation, which should lead to self-evaporation of all the black holes on a faster time scale than the self-evaporation of the cluster. Or at least that was the thinking up until a few years ago. Okay, so old clusters have no massive stars left. So the black holes are about 5 times as heavy as everything else. Right, so the black holes are typically around 8 solar masses, at least in the field. They might be heavier in the clusters. Neutron stars are 1.4, and so are the heaviest white dwarfs. And there are no normal stars that actually have fusion going on that are heavier than about 0.8 solar masses in a Glavier cluster. So the black holes are much heavier than everything else. And Spitzer in 1969, in a fairly abstract manner, showed that if you have a heavy population and a light population, the heavy population can self-segregate to such an extent that it basically doesn't interact with the light population at all. So it basically controls its own dynamics and sits in the center of the cluster. And at least at the beginning of the lifetime of a Glavier cluster, that's what should happen with the black holes. That they should make a subcluster of a few hundred stars sitting in the center of the main cluster. And if we go back to the timescales on a couple slides back, then the crossing time will be a lot less than 10 to the 6 years. The relaxation time will be maybe 10 to the 7 years. And the self-evaporation time will then be 10 to the 9 years at most, right? And as a result, you should end up having the black holes self-evaporate and not have any black holes left. Or at least that was the thinking. In practice, actually, this Spitzer instability should shut itself off after a certain amount of time, and some of the new numerical work suggests some other reasons why it goes even slower than that. Okay, so now let me talk a little bit about how we detect black holes and neutron stars and binaries. This is an image from the BinSim program by Rob Hines at LSU. He's basically written this computer program where you can put in the parameters for a binary system and it'll make a computer-generated artist impression that looks like that. So if you ever need to generate binaries, you can do this. You can make it vary in phase and make movies of it too. So it's a really neat tool. But it really does a nice job of illustrating what's going on. That when we have a low-mass extra-binary, which are the ones that we often can study the best, what we have is a normal star filling its Roche lobe and spilling matter into an accretion disk around a companion. And then stuff falls in, and then there's an enormous amount of gravitational potential energy being released as the stuff falls in. Half of it goes into making the rotation rate of the gas go up, and the other half goes into heating the gas. And as a result, around a stellar mass black hole, the temperature will get to about 10 million degrees, and that will then cause it to give off X-rays at about 1 kiloelectron volt. And if we make a survey of the sky in X-rays, especially if it's a shallow survey, essentially everything we see is stellar mass black holes and neutron stars in our own galaxy. If you start making much deeper surveys, then you'll start picking up huge numbers of quasars as you go deeper without picking up that many more neutron stars and black holes. But in the early days, this was essentially all we got from X-ray surveys. And from the scanning all sky monitors, we find any new transients that go off nowadays. All right, then the question is, how do we actually figure out whether we have a black hole or a neutron star? And what we want to do is measure the mass of this thing. And fairly well-established theory suggests that neutron stars can't be heavier than about 3 solar masses, and that limit may be lower than 3, it might be 2. So if we measure the mass of our compact object, and it's more than about 3 solar masses, we know we have a black hole. If it's much less than 3 solar masses, it's probably a neutron star, and there are usually some other things like surface effects that show us that we have a neutron star anyway. All right, and so the way we want to do that is we want to get an inclination angle for the binary and the orbital speed of the donor star. Right, so you can only measure the orbital speed in your plane. So if you have a face-on binary and you don't know that, you'll underestimate the mass by a lot. And that's why we try to come up with techniques to estimate the inclination angle. So the best is if you have an eclipse like is shown in this figure, right? Because then you can really nail the inclination angle. The next best thing to do is to look for what are called ellipsoidal modulations from this star. This star is no longer spherical, and its teardrop shape causes a roughly 10 to 20% variation in the amount of brightness, depending on whether you look at it this way or this way. And so if you measure this repeatedly over many orbital cycles so that you can filter out the effects of the light from this disk, then you can estimate the inclination angles and still get a mass even if you don't have an eclipsing system. All right, so now I want to talk about how we form X-ray binaries and star clusters. So there are three basic ideas about how you might form X-ray binaries and star clusters. So as I mentioned before, we know there are a lot more X-ray binaries per unit stellar mass in Glavier clusters than there are in other parts of galaxies. And so we need some kind of dynamical process to make those end up getting formed. Okay, so one possibility is tidal capture. And I just mentioned this figure is from a Funado et al. 2004 paper, which is about formation of binary planets. But all of the physics that was worked out for understanding formation of compact object binaries in Glavier clusters was then later applied to understanding how binary planets form. Okay. So tidal capture is controversial. The idea behind tidal capture is normally if you have 2 point masses and you're in freshman physics, if they're unbound, they stay unbound. But once you move beyond the point mass approximation, you may be able to excite tides in one or both of the stars and cause some of that excess kinetic energy to be dissipated in the envelope of one of the stars. So you need a lot of fine tuning in order to make this happen at a large rate without blowing up the stars by injecting too much energy into them. And so that's why this is fairly controversial. But there do seem to be some systems that are in an orbital period range that's well explained by tidal capture and not well explained by anything else. Another idea is direct collision between two stars, one of which is a compact object. And this is something that happens a lot more than you might think in a Glavier cluster. So you can do a quick calculation, and roughly 10% of all stars in a Glavier cluster should experience some kind of collision with another star at some point in their lifetimes. And so if you have a neutron star that smacks into a red giant, what it can do is the neutron star will then sink in towards the core of the red giant, and that will release a lot of energy that will blow the envelope apart, and it'll leave behind a very close binary with the neutron star and the red giant core. And the red giant core is basically a white dwarf. And we see some systems that almost certainly were formed this way. So there's an example, there's a system called 4U1820-30, which is in, I think, NGC 6624. And this is an X-ray binary with an orbital period of 11 minutes. Right? And at 11 minutes, the donor star is certainly some kind of white dwarf or white dwarf-like object.
Actually, excuse me.
Sorry?
I missed something. How do you form binary planets via this mechanism? You
I didn't read this paper that carefully, and it's been a long time, so I don't want to discuss that.
Okay, all right.
Yeah.
I don't know. I've never. Anyway.
Yeah. Okay, so now we're going to show the other movie. So this is a movie from Jamie Lombardi at Allegheny College, and the thing that was didn't have a red fuzzy thing around it at first is the neutron star. By now this is switched. The fuzzy thing is around the neutron star, and the white dwarf core is the thing that's orbiting around it really fast. You'd see the time counter on this thing is in units of days. So this is all happening very fast. These orbits are extremely fast. So at least in a smooth particle hydrodynamic simulation, you can actually make this mechanism work. And we see systems that really are hard to form in any other manner. Okay, and then the last mechanism isn't really creating binaries where there weren't some, but it's a way to get nicer binaries to form, and by nicer I mean ones where accretion is easier to have taken place. So you can have a wide binary with, say, 2 G stars sitting out in space, and if a neutron star flies near it, basically the most likely outcome of a 3-body interaction like that is that the 2 heaviest objects end up in the binary, and the binary is closer than the original binary. And this is something you can either do a bunch of numerical calculations and see this happens, or you can sort of think about what minimizes energy and think that's the most favorable thing. And either one leads you to the conclusion that this is a good way to get neutron stars into binaries, or get black holes into binaries, and get normal stars out of them. Okay. All right, now I want to talk about boundary cluster X-ray sources. So the Milky Way has 16 known bright globular cluster X-ray sources, and by bright I mean bright enough that the scanning all-sky instruments could detect them. And they're in 13 of the clusters. None of these bright sources is thought to be a black hole. But there are also a lot of faint sources in clusters, like cataclysmic variable stars that give off some X-ray emission, and even coronally active binaries. And normally you shouldn't have coronally active binaries in old stellar populations, but in globular clusters, you end up having a lot of close binaries, and the close binaries tidally lock the rotation of the stars and allow the coronal activity to survive a lot longer than it normally should. Right? And so the idea is that dense stellar environments lead to creation of tight binaries in these systems. This is an astronomy picture of the day from Craig Heinke at Alberta that shows 47 Tucanae in the X-rays. This is the same cluster that I showed 10 slides back. You can see a large number of X-ray sources in this cluster. But I'm going to talk mostly about extragalactic studies of clusters. So in the Milky Way, we just don't have enough objects. We only have about 150 globular clusters. We're probably missing another 100 back behind the center of the galaxy, as you can see from these figures of where the clusters are in the Milky Way. And the Milky Way's clusters are almost all metal poor and don't really span a large fraction of the range of properties that globular clusters can have. So if we want to understand what kind of properties cause a cluster to form an X-ray source, the Milky Way is not as good a place to look as other galaxies. And also, in other galaxies like M87 has 10,000 globular clusters. And if M87 isn't good enough for you, there's another 10 galaxies that are at similar distances that have almost as many globular clusters. So it actually turns out M87 isn't really good for this kind of work because the diffuse X-ray emission from the hot gas in the galaxy provides an enormous background. But some of the other gas-poorer giant ellipticals have tens of times as many globular clusters as the Milky Way and really make that a much better place to look. Right? And we may also need other galaxies to find rare objects like black holes, but as I'll wrap up by saying maybe not. Okay, so elliptical galaxies are much nicer for this than spiral galaxies. So this is a Sloan image of NGC 4472. And if you know where you're looking, you can actually see globular clusters right in the Sloan image with your eye. But also this is a very smooth light profile, and so this is very easy to subtract off and see what point sources remain behind. In the spiral, this is not so easy. And as I mentioned, there are much larger numbers of clusters in the ellipticals than in the spirals. This is an X-ray image from Chandra of the same galaxy, so NGC 4472. So this very central region has some hot gas in it. If I was making an image of M87, the whole field would be covered by the hot gas. And that's why, even though this is a galaxy with slightly fewer clusters, it's a much better place to do this work. But there are about 100 point sources in this image, and almost all of them are X-ray binaries. Probably 10 to 15 of them are background AGN. And this was a 40 kilosecond Chandra image, so about half a day. This is about the same number of low-mass X-ray binaries that we found in the entire history of X-ray astronomy in the Milky Way. And we did this in half a day, and we have a bunch of other galaxies where we can do similar kinds of work. So this really, I think, highlights how powerful Chandra is and using other galaxies is for studying this kind of process. Okay, so one of the things that we've done, and this is a figure from Mark Peacock's PhD thesis, and this is actually M31 data, is we wanted to know what kind of clusters make X-ray sources. So this figure is K magnitude versus, K magnitude on this axis, so the brightest one's on the right, versus collision rate, so some estimate of the rate at which stars collide with one another on the y-axis. And the black diamonds are the clusters with X-ray sources, the little pluses are all of the clusters. So we can see that the brighter clusters are more likely to have X-ray sources, but even at a given brightness, the clusters with higher collision rates are more likely to have X-ray sources. So we've really proven that collision rate makes X-ray binaries.
How did you estimate that?
So I had a UCURT data set of M31 with taken in very good seeing in service time. So again, this was only 4 hours of data on UCURT and basically made almost all of Mark's thesis. And by using that, the core radii of M31 globular clusters are similar to the seeing levels that we had in the data. And he was able to deconvolve the light profiles and fit King models to the clusters. And we actually had a bit of good luck that this was one of the very first service runs taken with UCURT, and they screwed it up. So UCURT has this paw print for the where the detectors are, and so that allows them to take large fields of view without electronics gaps. But the way they do it is they take one here, slide over, slide down, and then slide over. And then by the time they've taken this pattern of 4 observations, they've exactly covered your field of view. But they left out a cosine declination term. And so we ended up getting some of the stripes covered twice and some not covered at all. But then they went back and filled it in for us. And by the time they were done with all this, almost all of our clusters have been observed twice with different seeing conditions. So we're able to do a control check on whether the deconvolution actually worked, which was great because we have a plot of core radius 1 versus core radius 2 for the same cluster. And you can see that basically above 15th magnitude they line up perfectly. And then below 15th magnitude it's sloppy, but that's telling us where the statistics break down, not where the systematics are a problem. Okay. The other thing that's interesting here, and that's still relatively unexplained, is that the metal-rich clusters are much more likely than the metal-poor clusters to have X-ray sources in them, and this is something we've seen in a variety of galaxies now. And in some cases it's suggesting even that we have some supersolar metallicity clusters, because basically we're seeing an X-ray effect somewhere where the optical colors might have just been scattering things up to supersolar, but we're actually seeing even within what could have been scatter, the X-ray sources are much more likely in the more metal-rich clusters. Okay. Now there's some supernova physics that we can do with our findings too. So we found that the number of X-ray binders is proportional to the collision number and to the stellar mass. This is Michiel Smits, who was a master's student who worked with me in Amsterdam. So under normal supernova physics, you expect most neutron stars to be formed with a very large natal kick. So if we look at pulsars, they're typically moving about 200 kilometers per second. And that's way above the escape velocity from any globular cluster. So what we normally expect is only the low velocity tail of the kick distribution to be retained. And then what we would expect is that there'd be a very strong correlation between the mass of the cluster and whether it had a neutron star going beyond just the amount the mass contributes to the total number of neutron stars that were born. And we don't see this. We see we see essentially a linear mass dependence or a linear collision rate dependence and no additional dependence on mass that might be due to the escape velocity. And so one possible explanation for this is that a different kind of supernova is producing the neutron stars that get retained in the clusters, namely electron capture supernovae, which are basically supernovae that form without an iron core stage. And so there certainly isn't concrete evidence of that, but I think it's intriguing and worth additional follow-up. That this may be telling us that these electron capture supernovae really happen and that they don't produce large kick velocities. Okay. Now this is a kind of little side thing that Mark Peacock did kind of after he moved on to Michigan State, but based on some stuff he'd started during his PhD thesis. So we have plotted here our color versus metallicity plots for a bunch of different Sloan colors for M31. And I forget if I was talking to Ryan or Janelle earlier when I was saying this, but there was this nice Sloan data set on M31 that basically nobody looked at until Mark really got into it. And the curves here are all the different simple stellar population models for producing integrated colors based on stellar evolution and some stellar atmosphere modeling. And we can see they go through all of the curves very well, except for the G minus R, which they're all offset from where the main locus of points. And Mark had emailed me this plot and said, hey, do you know what might be going on here? And then the next day, this is when I was still in Southampton, Claudia Marstone was visiting from Portsmouth. And I showed this to Claudia, and she said she already had solved this problem because it came up in the luminous red galaxies. And the solution was basically that everybody, including her up to that point, was doing the stellar atmosphere modeling wrong. And so all the stellar population stuff was right. And you just had to modify the way you applied stellar atmospheres to your stellar population models, and then you would get a good fit here. And that took away the need to put a bunch of extra star formation into the luminous red galaxies to explain what was going on with the bluer colors for them. And so this gave us a really nice concrete test of something that we weren't even aiming to work on. Okay. This is another thing that Mark did fairly recently. And this doesn't involve clusters, but it kind of goes along with doing galaxy evolution as a side effect of what we're doing here. So I mentioned before that there have been these claims of very strong initial mass function variations in recent years. And so what we did was we collected a large sample of elliptical galaxies, all of which had different velocity dispersions, which is the thing that the initial mass function is supposed to vary with. And we plotted the X-ray luminosity, number of X-ray sources per unit stellar mass versus X-ray luminosity. We can see all the X-ray luminosity functions are basically the same. And then what we did was we said, okay, let's look at the number of X-ray sources per unit stellar mass and compare it with the velocity dispersion. What we can see is that we have one outlier here, which is in the middle of the diagram, which we don't understand right now. This could be an age effect. But there's no systematic trend of the number of X-ray sources versus the velocity dispersion. And this is the prediction if we vary the initial mass function. Right? Because if you vary the initial mass function, you're varying the fraction of the stellar mass that's locked up in black holes and neutron stars, and you should see some effect of that on the number of X-ray sources that are produced. So I think this is actually one of the strongest pieces of evidence that this IMF stuff probably isn't real. Okay, now I want to get back to HC 4472. So we'd seen this difference between the red and blue clusters, or the metal rich and metal poor clusters, for whether they produce an X-ray source, and we wanted to get more data on that. But it turns out the metal poor clusters tend to be much more spatially extended in their distribution than the metal rich clusters. So what we wanted was to get a wide field of view observation in the X-rays, and so we used XMM Newton to do that. And we still haven't finished the project that was the nominal goal of the proposal, because we get distracted by something that turned out to be, I think, a bit more interesting, which is this one source here. So we saw a very bright X-ray source with a luminosity of about 10 to the 40 ergs per second, which is well above the energy luminosity even for a stellar mass black hole. And it was in this optical source. So this is a Glavier cluster in the optical out at that distance. So when you go to 16 megaparsecs, they don't make pretty pictures anymore. So they basically look like point sources. And I should mention, especially since Louis used to work at Indiana, Kathy Rohde has given me a better image of that, and I just haven't gotten around to putting it into the talk. So, but she saw me show that once and was like, "I made a much better image than that." I was like, "Sorry." Yeah, anyway, so this source was also highly variable. So up until recent years, there have been very bright X-ray sources seen in extragalactic Glavier clusters. The problem was always that you could have 4 or 5 bright neutron stars in the same cluster. You know, we have one cluster in our own galaxy that has 2 bright neutron stars in it. So if you just see a high luminosity and say it's above the energy luminosity for a neutron star, you can't say it's a black hole just yet. But this source varied by a factor of about 5 in X-rays in the span of a few hours. And that's something that a collection of sources will not do. Right? And so then we could prove that essentially all of the emission had to be coming from a single bright source. And now we have a single bright source well above the energy luminosity for a neutron star. So it basically has to be a black hole. The X-ray spectrum is dominated by a 2 million Kelvin blackbody component. So this is actually softer than black hole spectra usually are, but you know, it's similar to what we see in the ultra-luminous X-ray sources, which we think are stellar mass black holes accreting at just slightly above the energy luminosity. So maybe a factor of a few above the energy luminosity. At that point, they get puffed up by radiation pressure, so the characteristic radius becomes much larger, and they blow off strong winds because they're super Eddington. So that's what we think is going on with this system, and partly because it turns out all the variability was below about 0.7 keV. And that's something that you can explain by instabilities in a disk wind being blown off, because below 0.7 keV is where you get your carbon and oxygen edges. And so if you have a disk wind that's intercepting the light coming to you, and you vary the amount of the disk wind, you'll have variable absorption that'll cause that part of the X-ray spectrum to vary, but you won't be varying the kind of central engine very much. Okay. So one thing you might be wondering is, like, how did we actually know this was a Glavier cluster and not just a background AGN or a star or something? And the reason is we had a VLT optical spectrum. So this is our original spectrum, and we were able to cross-correlate this with templates for Glavier clusters and get a velocity for the cluster that was at about, I think, 1,400 kilometers per second, so something totally reasonable for the Virgo cluster. But then I got worried when we saw this in the spectrum. So this is an extremely bright emission line in the cluster spectrum, and I did a calculation and I found it was unlikely but not impossible to have a background AGN lined up with a Glavier cluster because we had looked at so much solid angle. So I get really nervous. Now it turns out when we adjust for the redshift of the cluster, this line is at 5030 angstroms in our rest frame. It's at 5007 angstroms in the cluster's rest frame, which is one of the very strong lines of oxygen 3. Okay, here's a Keck spectrum, the same thing. Okay, so this is that line again. Okay, so this line has a velocity width of about 2,000 or 3,000 kilometers per second. And that's actually consistent with what you expect for a disk wind being blown off of a very high accretion rate X-ray source.
Do you understand all the spectral features in the previous graph?
A lot of that's noise.
Really?
Yeah,
Ugh.
that is a low signal and noise spectrum.
Okay.
This is a much higher signal and noise spectrum. Okay, so one of the really interesting things here, though, is look how strong this oxygen 3 line is. Now look at H alpha and H beta. Those are in absorption. And so we've done a bit of modeling, and what we found is that the ratio of the strengths of the oxygen to hydrogen lines are at least a factor of 30. There's a little bit of uncertainty because you have to subtract off the cluster's starlight spectrum in order to do that. But we can't come up with any reasonable photoionization model that does this without making it a very hydrogen deficient system. But fortunately, we actually have an explanation to do this. So the most obvious way is to make the donor star in this binary a white dwarf. So make it one of these ultra-compact systems. And if we do that, it has to have an orbital period of about 5 minutes in order to produce the X-ray luminosity that we see. We tried a few other ideas, like it might just be a nova shell in the same cluster that's independent of the X-ray source, but the variability information that we have now rules that out. Okay. All right, and so this actually has some impact for brain world models. So this is these ideas that gravity is extremely weak compared to the other fundamental forces. One of the ways to solve this problem is by having a bunch of extra dimensions, and we're just sitting in a 3+1 dimensional membrane in a much higher dimensional space. But Hawking radiation is actually way more efficient in at least most of these models than it is in standard general relativity. And so if you take that into account, a stellar mass black hole that's 10 gigayears old puts a constraint on the size of the extra dimensions of about 3 microns. And that's about an order of magnitude better than what you can do with torsion pendula. So we actually have the best constraint on extra dimension sizes from seeing old stellar mass black holes rather than from anything you can do in a laboratory.
I'm sorry, I did not even, I'm sure you said all the right words, but I didn't understand that argument. Can you go
Okay.
just a little more slowly?
Oh, okay, sure, yeah. So Hawking radiation depends on how much parameter space you have to evaporate things into.
Yes.
And so if you open up that parameter space by adding a bunch of dimensions, black holes should evaporate a lot faster than they evaporate in standard general relativity. So if you believe in these extra dimensional spaces, the seeing old stellar mass black holes gives a maximum size for any extra dimension. So seeing a 10 solar mass black hole that's 10 gigayears old says those extra dimensions are less than about 3 microns. And with torsion pendula, you can only prove that they're less than about 30 microns. Okay? All right.
But so the old stellar mass black hole should have evaporated.
If you believe in these extra dimensions and they're big compared to 3 microns.
And if they're not accreting or growing.
So that's something that Dimitris Saltis has kind of worked through this. And if you make them accreting, then they were even smaller when they were born. And it basically, if you work through all the possibilities, the current mass still gives you a good constraint. You can't get around that by making them accrete. All right, so I'm actually going to skip this slide because I think I'm running a little fast. But I want to talk a little bit about the galactic case. So this is a relation between radioluminosity and X-ray luminosity for stellar mass black holes. And this is an example of one of the kinds of things that you can do with individual systems showing a nice track here that you can't do in AGN. In AGN, you have to amass big samples and think about your selection effects. So we have this nice correlation, especially down at low luminosity. And basically one thing it tells us is that if we see a moderately bright radio source and not particularly bright X-ray source, it's hard to make it anything other than a stellar mass black hole. There are a few pulsars that sit around here in this diagram that are things that go back and forth between being pulsars and X-ray binaries, but up on this track and especially down below, it's really hard to make them anything else. And so what we started doing is taking deep radio observations of nearby Glavier clusters. Okay, and this is from M22. We saw 2 radio sources right in the core of the cluster, and they're also both flat spectrum sources, which not very many background AGN are. And neither one of them has an X-ray detection, so those are both things that have very high ratios of radio to X-ray and are flat spectrum sources, so they're good black hole candidates. And then we have this object in 47 Tucanae. We have, I think, about 8 of these in total now that are good candidates. There's a couple of them that are isolated enough that we can get radial velocity curves for them, so we're working on actually trying to prove that they're black holes rather than just saying they fit a relation that makes them maybe black holes, but that's not quite there yet. All right, now, as I wrap up, I just wanted to mention how we avoid this Spitzer instability that says we should kick all the black holes out of clusters. So even in the simplest case, first of all, the Spitzer instability only ejects 90% or so of the black holes, and that's similar to what we think the retention fraction for neutron stars should be. So then actually the black hole to neutron star ratio shouldn't be much different than in the field. So that's one thing. And then the other thing is that Megan Morsher, who just finished her PhD at Northwestern, has done some really nice numerical work. And one thing she's pointed out is that there's actually a spectrum of black hole masses, and only the heaviest black hole masses actually segregate into this subcluster. And when they get ejected, then you're taking mass away from the very inner part of the cluster, and that perturbs the velocity distribution for everything else and causes the cluster to puff back up. So, and that dramatically slows down the process of the Spitzer instability kicking everything out. Right? Spitzer did this calculation for 2 masses, and when you start thinking about a broad range of masses, this effect works, but it doesn't work anywhere nearly as fast. And so I think that's a real breakthrough that explains why we have so many good candidate black holes in globular clusters. So I'm going to leave my conclusions up and go to the questions because I think I talked a little bit too long. Okay.
Great. Any questions?
So another type of binary system is a planet orbiting a star. Like, what's the status of planets in globular clusters?
Okay, so there's one that we know of, which is around a pulsar in M4, but that could just be a lump of something that got formed by the pulsar. In 47 Tuck, there was this planet survey thing done, like right when the transits were discovered. Ron Gilliland got them to do this continuous long observation of 47 Tuck with HST, and they found 0 planet transits in it. But there's 2 possibilities there, right? So there's also a bunch of stuff that's been done that suggests that metal-rich stars are much more likely to host planets than metal-poor stars. And so it's not clear whether the planets are all getting dynamically ejected, or they're free-floating planets so they don't transit anything, or 47 Tuck is metal-poor so it doesn't have planets. So I think all of those are viable possibilities with what we know right now.
Is there any campaigns to do something similar?
Uh,
Because this was over 10 years ago.
Yeah, it was. It was when I was in grad school. It was like 15 years ago. Yeah. M4 was in the Kepler field recently, and I know they just put a big mask over most of M4, or at least the outskirts of M4. But the problem is in the inner parts it's still too crowded because Kepler has big pixels. Yeah, I haven't heard of. I mean, that was a lot of orbits that they did use for that, and then they didn't find anything. And I think the metal-rich clusters are mostly the things that are also heavily obscured, so it's kind of harder to do it there.
I see.
I think it's an interesting idea, and so I don't want to say it's not a good idea.
Yeah.
But I think there's a bunch of technical issues that might make it hard to do it right.
Have any sort of theorists worked out these dynamical sort of models? Like, do Heggy's law apply to?
It should apply to everything because it's something you can just do in like 10 lines of algebra.
Yeah.
So,
Okay.
yeah.
One of the biggest mysteries of globular clusters is why they have such uniform metallicities. And one way around that is to assume that the globular cluster formed out of a much, much larger object.
You mean internally?
Internally,
Yeah.
yes.
Yeah.
And so if it actually formed out of an object that was some 10 to 100 times
Yeah.
the size of the present globular cluster, wouldn't that mean that there could be many much larger black holes that you would expect in the cluster that has nothing to do with the IMF that you would see in the globular cluster now?
Okay. So let me make sure I understand your question. So I think there's some limits to how big you can make that because then you overpopulate the halo with just stripped globular clusters.
Yeah, that's, well.
I think that's some of the stuff people have been doing recently is starting to push those limits.
Yes.
But
still, the numbers they're talking about are about a factor of 20 larger than the present
Yeah.
globular clusters we see.
Yeah.
Because the halo is about 95%. The number of stars in the halo are
Yeah, that
more
sounds
than
about right.
globular clusters.
Yeah.
So the object that you're looking at when you're globular cluster actually was a much more massive object,
Yeah.
which had a significant number of more massive stars that,
Yeah.
that formed and blew up and produced metals.
Mhm.
Wouldn't those stay in the globular cluster? Wouldn't therefore you see a different population of black holes in the globular cluster if it came from a much larger object?
Okay, so that depends on whether you think you have mass segregation already at the time when the stars are blowing off. And if you're talking about making something much bigger than the relaxation time scales, you're going to get long. But there are some suggestions of primordial mass segregation that in the formation stages of the cluster, you just form the most massive stars at the center. So if that's going on, then I think your scenario is viable. But I think it's required for that to be going on for your scenario to be viable.
I'd just like someone to come up with an observational prediction of this particular model, the globular clusters formed out of such large objects.
Yeah.
Maybe, I was thinking maybe in binary stars, or you don't think there is something that such a model would predict.
I think it's complicated because so much happens to the cluster that it basically forgets all its initial conditions. But I mean, what I've seen lately with people talking about the clusters being bigger is actually to explain the different metallicity populations. They're subtle, but
No, this is
Is
actually
this old stuff?
This is actually the cluster is the initial object is so large it holds on to all of its metals, and it mixes the metals together, and then the object in the center is what forms the globular cluster.
okay,
So
I
it's
see.
kind of like
Okay.
a mini galaxy.
Okay.
But in that situation, you will form a significant number of black holes early on.
Yeah.
But I don't know what happens to those black holes. They just leave the cluster, or they fall into the cluster.
I mean, the other thing that could happen, and this is something that there's a paper Nathan Lee wrote that I'm a co-author on, is if you still have a lot of gas around when you start forming those black holes, they could actually bond to accrete and grow just from the intercluster medium. So if you're at molecular cloud densities, the accretion rate onto a stellar mass black hole is not trivially low. And that might be a way that you could get intermediate mass black holes in clusters if they actually do exist. I think right now the observational evidence for that is quite scant. There are a lot of claims out there, but they're all kind of 2 sigma, and all the accretion signatures that you might expect are missing. So yeah, I don't think I have a good answer to your question, but I think it's an interesting question.
Yeah, this model was created in order to explain the oxygen and sodium abundance variations in the stars.
Yeah.
And which you don't see in the field.
Yeah.
So in order to hold on to that stuff, they required a much larger object.
Yeah, no, that's, okay, no, so I know that, yeah, so now I think, okay, I think we were in violent agreement a minute ago. Yeah, so I know those papers. Yeah, and there's another nice explanation for all that stuff, which Nate Bastian has come up with, that doesn't require a huge outer halo, which is that basically the pre-main sequence lifetimes of the low mass stars are longer than the total lifetimes of the massive stars. And so you start polluting from the massive stars, and some of the main sequence stars have orbits that take them into the polluted region, and some of them don't, and that's why you can get nice bimodal distributions. So I like Bastian's idea better because it doesn't require that the whole halo be made up of remnants of globular clusters, which I don't think, I'm not sure exactly how you go about testing that, but it seems a little perverse to me to say that the halo doesn't form any stars except in globular clusters.
Great, well, let's thank our speaker again.
No, there's yours. And I can just leave this here, right?
Yeah, you can have your-
And actually,